Right, here we go. So there's two parts to this. Usually, a lot of the questions deals with either trying to figure out the formula or write the name. So for example, like a typical ionic compound would be this one, sodium chloride. We've seen this one many times. Yes, it reminds me now, you were asking me last week, okay, why chlorine gas, which is this formula, is poisonous, but this thing, together with the sodium, is not poisonous, right? And I remember I didn't give you a very good answer. I don't know if today I'll give you a better answer, but it goes like this. So, now, the only way I can explain it is by thinking like this. So you got, basically, if you were to draw the Lewis dot diagram, right? Lewis dot diagram for this one. The key thing is, this is not an ionic compound, okay? But I can still draw the Lewis dot diagram. It will look like this. I'm gonna use X for this half. 1, 2, 3, 4, 5, 6. 7. Looks like this. So the dots are belonging to this chlorine, are the electrons for this chlorine, X are the electrons for this chlorine, and these two are in between the two electrons. So this is how both satisfies the requirement of full valence. They share electron. I'll get into that later on, okay? But this is the entire compound. This is how they look. There are two. But for this, you know, we learned how to draw these ionic ones for Lewis dot. It just looks like this. Okay. So why is this not poison? Why is this poison? Well, this comes in two. Okay, so when you're talking about the poisonous chlorine gas, like on the molecular level, it's always coming in pairs. These elements, the elements comes in pairs. That's what makes them poisonous. It's different than this one, which in ionic compound is single chlorine atoms. This is a pair of chlorine atoms. That makes a huge difference. In fact, we need a lot of this. Okay. I need a lot of this, and there's a, as far as I know, all right. This, if you don't have this, I mean, it's not like I should say this is not poisonous. This is not only is it not poisonous, our body needs this for a lot of normal activities that we do. For example, like breathing. Okay. People who have a health condition, you probably have heard of this condition called cystic fibrosis. Children sometimes, like, you know, unfortunate children, they're born with this disease. They can't breathe. That's probably because of the issue with their chlorine ions. This chlorine ions can't get to where they need to be in the body. So that's why they get this disease. Look it up. It's a very cool genetic, you're born with it.
So you die?
You don't die right away, but like you will have a lot of problem breathing. So like children usually don't survive past like age 14. Like it's very saddening. It's a very it's a big problem in people who have these things. So yeah, so this is not only not poisonous, it's essential for your body. That's why, same thing with this sodium ion. That's why we eat salt to get both of them. It replenishes both things. That's why, you know, contrary to popular belief, your mom or your dad might tell you to like reduce your salt intake, not to make your food so salty. You tell your mom, no. Enzo told me you gotta have both of these because it's important. You don't wanna, it's not the case when it comes to healthy eating. It's not the case. Oh, you always want to eat less salt. No. It depends on certain individuals. A lot of people some people need to make sure they get enough of these ions, right? Anyway, and then of course this is poisonous. This was built into a weapon in World War I, and a lot of people died. So anyway, I got sidetracked. Let's come back to, yes, we started off answering your question about why this is poisonous. So this is the compound, and so sometimes the kind of question you will be dealing with involves either they give you the element, they give you the formula, and you write down the name. Or they give you the name, for example, another one is like potassium, they give you a name. They give you potassium, they will spell the chemical name oxide, and they want you to write down the right chemical formula. Yes? Anything? No? Okay. Alright, so these are the two types of questions that we'll be dealing with. And we're going to do a lot of practices on these. Last time I told you we were learning how to write the subscript. And I showed you can check using like simple math. And you can also figure it out by knowing the charge on the elements. So let's do another quick practice. So we have, let's say I am going to make an ionic compound with aluminum and oxygen. You guys don't have the periodic table, do you? I have two extra ones.
I have one.
You have one, okay. You can take this one. So I'm making a compound between aluminum and oxygen. So now your task is to figure out how to write this formula. Obviously, you know that the rule says, right, to write the formula, the metal one usually is on the left side. So you write that first. And then comes the non-metal. But the trick really, that's not all of it, right? The trick is knowing what numbers to put underneath. And we learned the crisscross. Last time I showed you that what you can do is figure out the charge aluminum would become after becoming an ion, and figure out the charge on an oxygen after it becomes an ion. So tell me the charge on this one very quickly. This one?
3.
Yes, 3 is positive or negative?
Positive.
Okay, so you write this down, and this one?
-2.
-2, okay, good. So after that, you just put this number over on this side, put this number over on this side. That's what's called a crisscross technique. Right, this ensures that you end up with the right subscript. So there's your compound. 2, 3. Well, you can then prove it with like charge, balance, whatever. We did that last time, right? But this is the quick and easy way to do it. All right. So that's half of it. That's for the first part. The next part is chemical name. So let's give you a different compound. Let's have you do sodium. Let's have you do the name of this.
Wait. Do you just say it out loud or?
Okay, so you write it in. Try practicing writing these chemical names. The spelling counts. Okay. bromine is right here.
It's above iodine in the 7th.
Yes. Alright, so it goes like this. Sodium bromide. Alright, make sure to replace the last couple letters with IDE. Are you okay with this, David?
Mm-hmm.
Okay, so IDE ending on non-metals. There's a joke about this element, about this compound. It goes like this, alright? So it says like, you wanna hear a joke about sodium bromide? And then the other guy says, nah bro. You get it? My wife is not working. Hold on, I'll be back. Can't find your mom. So I guess we'll do the joke after, right? So, okay. So let's keep going. I'm gonna send this copy slides to you, and I'll make you guys do some practice from here. Right? But, let's move on for now. I want to show you. I wanted to show you a chart, right? So if I can have your attention on this. This chart tells you, okay, some metals have more than one type of charge. Mainly the ones in this transition metal group right here. We know that, okay, anything here is going to be +1, +2, +3, and negatives. But the ones in the middle, certain elements like chromium, these ones here, it can have more than one charges. This has nothing to do with their valence electron. So the way you know exactly what charge they can be, there's no rule for it. And so this part is really like, you gotta know it. Well, you don't have to know it, but I'm just explaining to you why they are like 2 + 2, why some of them are +6, +4, blah blah blah. It's just how they are, and the fact that they have more than one possibilities, it's also just how it is. And so when we are naming these ones, which means, let's take for example iron over there in that chart. Iron can either be +2, can either be 2+ or 3+. Yeah.
But if it doesn't have a full valence shell, won't it just react again?
Well, it definitely won't react. I don't think it has full valence. Either one of these atoms don't have the same valence. The difference between this one is that this one lost one extra electron. That's why it becomes 3+. And it's okay too. This is still a stable thing. This is also stable. So because it doesn't have anything to do with valence electrons now. These electrons are lost not on the valence shell. The electrons are lost from inside. This is only something special for transition metals, which we're not going to get into too much about, because that's all I want you to know. It's just to get familiar seeing some of these metals having multiple charges. Which means when you have this element with multiple charges, it can form different compound even with the same partner. So let's take oxygen being the partner over here. Oxygen is always -2. So if this combined with this, you get one formula, one type of chemical formula. If this combines with this, you get a different type of formula. This one. Because of the charge, I mean, because of this going on, 3 goes here, 2 goes here. So you can see this compound is different than this compound. Because of the numbers here, they're different. And also because it's not the same ion. These two are not the same ions. And therefore the entire compounds are not the same. Okay. But the name, so how are we going to name them? That's the bigger question here. Because look, we said, okay, you take the name of this iron, you take the name of this oxide. Now, this is going to be the same, iron oxide. Isn't that a problem then? The name, based on based on what we have learned so far, the name doesn't distinguish these elements, these compounds apart. So what we're going to do is we're going to add some numbers next to iron to specify what charge the iron is. So let's put, the way to do that is by adding Roman numbers after the metal. Iron 2, this is the Roman number for 2, and 2 is symbolizing the charge, and here is iron 3 oxide. And then if it's 4, if you deal with another element that has positive 4, then like here's 4, 5, 6, 3, 2, 1, using Roman numbers. And so how we say this element is this compound is iron 3 oxide, iron 2 oxide. Okay. Yeah, and same thing applies for the other elements with multiple charges. Okay, the more you do it, the more you see these elements, the more you should remind yourself whenever you run into a compound that has these elements, you want to add the numbers right after. Okay. Questions? So let me give you a few examples. Pick one from the list, from the table.
Do you want to pick?
I'll pick for you guys. Chromium 3. Okay. We're just focusing on this one, not the other one. Chromium can also be another charge, right? So chromium, and I want to make a compound. Let's say chromium mixed with sulfur. No, let's mix it with fluorine. Okay. Alright, go. Figure out this one and this one. Finished? Okay. So chromium, like this.
Oh, I'm gonna go 1 next to chromium.
Oh, okay.
So.
Yeah, make sure don't ever write a 1 next to the. If it's a 1, you just don't need to write it. Same thing with the charge. If it's only positive 1, you don't need to write a 1 next to it. Like, think back to math, you don't put, if you use 1 times something, you don't use the 1, right? It's unnecessary work. So this is the same idea. So name is going to be chromium 3 fluoride, right? Okay. All right then. Let's move on. So this chart will be handy for you. Now some question will be tricky, and it will put if you get a bunch of the questions all at once, it will mix some of these in, and it's your job to know that you're supposed to add numbers afterwards. Like it will mix it with you get a bunch of these, and some have the numbers, some don't. So that's why I think at school they will give you a chart, so it helps you to know when to add numbers, when to not add numbers. All right. Got to this. Here are some more practice in here, so I'll get you guys to do some. Next part is what's called polyatomic ions. Polyatomic ion, just like the name suggests, it is still ion. Okay, keep that in mind. It's always ions, and which means it's gonna have a charge, and then poly means more, right? More than one. So it's an ion group with more than one ion, or with more than one atoms. Okay. That's as basic of a definition as I can come up with. Polyatomic ions. Okay, an ion group. With multiple atoms.
Isn't that just what an ion is?
No, the ions we've been dealing with up to this point has only been one. Okay, I know what you mean. So here you can say, okay, this is a positive charge, it's a negative charge, and they're in a group. Well, I'm saying all the atoms in this group share one charge. I'll show you an example. All right, it's different than this in the sense that here only the sodium, which is one atom, has the positive charge. The chlorine has a different charge, so they are separate ions. Here I'm talking about an entire group of atoms with one charge. Right? Usually when we say an ion, we mean either one atom or a group of atoms that shares one charge. So let's go to the next slide. Yeah, just like any other ions, it cannot be negatives and positives. So here they are on this list. I will write a couple on the board too. guess that's as much as I want for now. So you're looking at this group, you can see how the charge is not on every single atom. And you start to see these numbers, but all I want you to do is treat this as one big ion. And this big ion has an overall charge of -2. Make sense? So we're not talking about just one atom with a charge. It's a group of atoms. In this case, the sulfur, and 4 oxygen is in total 5 atoms. The 5 atoms together carries a -2 charge. And this is what we mean by a polyatomic ion. 5 atoms with a charge. Right? So all these ones I've written here are examples of polyatomic ion. Yeah. At first, when you see them, it gets pretty strange. But all I want you to pay attention is to try to treat them as one. Treat this as one, everything as one. As one unit. Right? Which means you don't actually need to worry about the charge on each individual atoms. That doesn't really tell you much. All you care about is the charge overall. Right? You'll notice how a lot of them involves oxygen, and it's true. Some of them, most of the ones have oxygen. Here's a couple more from there. Cyanide, right? Cyanide. This is also a polyatomic ion. Ammonium. This is one with a positive charge. And then there's a few ones out there. Right? We can still do the Lewis dot diagram for these. Actually, no, not really. Okay, so, but like the way you visualize them, the way you try to kind of imagine how they are, like a 3D point of view, like you just say, okay, I have a sulfur, and then I have maybe 4 oxygens. And somehow there's a bond within this group. We don't really need to get into that, but somehow, okay, there's a bond, maybe even a couple more bonds, and then this entire thing is 2 minus. That's the idea of these polyatomic ions. It's just bigger, right? Rather than having only 1 oxygen, 2 minus, this is a bigger one together. Okay. How about how we're gonna name them? Alright, so start with this one, SO4. We're not gonna name them separately. We're not gonna call them, okay, sulfur oxide, and then no. This one is called sulfate. I would advise you to, let's go back up to this one. I advise you, maybe you will write out all the ones that appeared on my PowerPoint, and then we'll make the other column the names. So SO2, 2 minus SO3, 2 minus PO4, 3 minus PO3, 3 minus PO3, 4 minus PO2. let's write their name. Write this part in. I'll go like this. So I focus on how I fill them in. Phosphorus. Phos. Okay. Let me write down this part. Okay. Alright. And then I'll fill out the suffix. Not too bad, right? There's some sort of pattern going on. All these are named after the the element on the left, and just like how we said like non-metal ending is ending with IDE, it's the same idea. We keep the first half of the word solve, right? Solve, the original word, but in this case, instead of putting IDE, we're putting an ATE. And you notice how when it's 4, when the oxygen is 4, it's ATE. When it's 3, it's ITE. When it's 4, it's ATE. When it's 3, it's ITE. And then all of a sudden, okay, when it's 3, it's ATE. When it's 2, it's ITE. So the pattern here is whenever, I want to say this. Treat this as the default. These three. Whenever the variation decreases the number of oxygen, you switch the name from ending ATE to ending ITE. You look pretty confused. So, does that make sense? So if it should originally be 4, and that's gonna be your default. Once you see a compound, not a compound, when you see an ion with 1 less than it should be, then the name, the only difference is the suffix change. And I can add on a couple more. So here, these ones. So this will be chlorate. This one would be, what would this be called? Help me finish the rest.
Chlorite.
Yes. Good. Okay. Now this is the part where you want to memorize. For nitrogen don't have NO4. It only have NO3 as their default. And so you see NO2, that's 1 less than default, which makes it a nitrite. Okay. Anyway. Alright. For this one though, some of these ions, they have more variations. So we've shown here, this is one variation. Right? Every single group have 2 variations. Some of them have more. You will start to see this one can have 5, this one can even have 2. But the charges are the same, always the same. Okay? And also, you'll also want to remember, the other thing you want to remember is treat these as a family. This family has one certain charge. This family has another different charge. Here's -2, -3, -1, and this family is all -1s. And how about this one then? Well, as it turns out, it's still chloral, but then there is ITE. you start adding prefix. Here, hypo. Here, perchlorate. Like that. These are also Greek, I think, suffix. Hypo means low. Low. So like low, I think, is trying to indicate low numbers of oxygen. Right. So, I'll come back to here, but this is that list. Question? You notice a lot, I mean, all of them that I've shown here has both, is usually between two non-metals. Most of the time. There are some ones, there are these ones that are exceptions. Okay. They don't follow any of these rules we just learned. They're kind of like a single case. They're like a single case based. Cn is cyanide. And you might wonder, why are there so many exceptions? Well, I believe the theory is like this. When people first discovered these compounds, they named it whatever. They didn't know that it comes so many variations. So they don't have any system to it. They just name it whatever they wanted to name. And then this name stuck around. So we keep using the old name. That's why you have so much of these exceptional, like odd ones. What else? You have cyanide, this one is hydroxide, this one is ammonia. Now, this by no means is a complete list, okay? This is just me trying to help you out and identifying the pattern, okay? And also the same thing for the exceptional list. The list goes, I'm just only showing you a few, just making you aware the naming it's not clear cut. So many of these have odd names, alright? Okay, so sometimes you'll see hydrogen added in front. One example is this one, carbon minus. Now, in the beginning it's just carbon and then oxygen. 2 minus, this is called carbonate. Right, it's all there. Right, carbonate, and then you can add an H to it, and then it will become, adding an H. It's now minus, it's now bicarbonate. This word here, Bi. Okay. That's just same thing for this one. You can see on my slide. Sometimes you can see H attached in front. And the whole name changes. Okay. All right. That's pretty much it. That's all I wanted to say for polyatomic ions. What else? So, now notice how each of these has a charge, and I said they're a group, which means this being one group having -2 charge, it still can form an ionic compound, right? This being the negative side, you can also then bring in a positive side to make a compound, and it will still be an ionic compound. It's just that this time the negative charged part has more atoms inside, so that the entire formula will look longer. So example would be, let's take sodium. Okay, let's take this one, like that. That would still be an ionic compound because it has the metal group, and there's your non-metal group, right? Remember this one on my slide? This one is a positive charge. Okay? This one is called ammonium. And because it's the special one being a positive charge, it can form compound with any of these. And so you end up with a formula of 4 elements. So you can make a compound that's like NOH4 PO4. Right, this is the basic idea. Now here's the next part. Because the charge hasn't balanced out, right? PO4 is 3 minus, NH4 is positive. So what do you have to do? You have to then use the crisscross, okay? Here's positive 1, here's minus 3, so the 3 needs to go here. The 1 needs to go, well, the 1 is already there, so you don't need to remember, but the 3 go here becomes a problem, because then this 3, should it become a 7 then? So there is the part that, so here's the next part, right? This doesn't become a 7, the 3 is outside. And to make sure this 3 applies to every single atom inside, you put a bracket like this. And then you put the 3 outside of the bracket. Just like math, right? When you do operation, you use brackets to mean that, 5 brackets, 5 times 8, whatever. This means this 5 applies to all the numbers inside. The same thing with this formulas. Okay. Right. So we got this one. We got the polyatomic ion. We got the metal side. We took care of the metal side, right, where some of them can have more than 1 charge. We took care of the non-metal side, where some of them can come in groups. Now we can bring it all together. You can get a compound that looks like this. You get a compound that looks like this. Iron and okay, iron. Iron sulfate. Like this. You get a compound like this, and then it's a lot of stuff going on here. A lot of letters, some brackets, some numbers. Looks kind of scary, right? Because the name is even longer. So what's special about the iron?
It's transitional.
Yes, but what did we just learn about them? Their charge.
They're different.
They can have more than 1 charge, right? What do you think is the charge on this one? Like looking at these numbers, you can work backwards. Remember the crisscross? Now uncross them. And you can figure out the charge.
-3. +3.
Yes, +3. Is that what you all got? Okay, so basically when you see this, you want to make sure you find out the right charge, because then that determines what number you want to add, determines what Roman number to add. So this one is iron 3. And then you write out this name, which is here, sulfide. And there you go. Voila, your answer, okay? Now, like if you're not very careful, like you're doing math, it's got many steps, you want to try to reach the final answer. This is the same thing, there's a lot of things you're processing. First you're processing the charge, and then you're trying to write down the number, and then you want to also figure out what's the name of this, right? Because you want to know, okay, this is not the default, this is one less oxygen, and so this should be called sulfide. And boom, all of a sudden you get the right answer.
So you ignore the oxygen?
Yes, so you can see how these names, right, once they're named as a group, that's the name. You don't see the spelling of oxygen anywhere in here. Okay, let's have you name this one, please. So remember, this is one group. You're treating it as a group, and this is the other group. Okay. I'll write this again. So here's one group, and here's the other group. Like start looking at them not as individual elements, but looking at them as like blocks, right? And we just learned that this block is called this, right? This block is right here, go back up, right here, this block. Okay, so what you want to do is you want to start learning how to kind of break down a long formula like this. Like I just did it here for you. This is one part, this is the other part. And this part, now you see the 3 here, right? But the 3 really just was there to balance out the charge. You know, like the 3 is meaning you got 3 of these. 3 of these. Make sense? So basically, this part is ammonium. Okay, it's in the slides there. okay, Crystal?
I don't know what to do.
Okay, like you're stuck on this part? Okay. How far back should we go? Are you okay with these?
Yeah.
Are you okay with these?
Mm.
Like these are the exceptions, right? They're the ones on my slide, which doesn't follow the naming pattern over on this side. You know what? Forget. We'll just leave this one out, okay? Because I'm jumping too fast. I do that, and then student gets confused. Let's go back. So practice this one, right? Erase this. Did you all write this in your list? Write these into your list. Okay. Into your notes. Like here you wrote this list, and then now you can create another list to put down these ones with the exceptions. Okay, these are the exceptions. Okay, so you did that. Good job. Alright, so now, like all things when you're learning it, right? You're learning it piece by piece, but then you gotta put it together and apply it. And this is the application part of it. Okay. When I take this and then use it to make an actual ionic compound, alright? We are still talking about ionic compound. Okay, we're just looking at some more complicated ionic compound. But this half is the positive side, this half is the negative side. So this half, as we learned, is called ammonium. And this half, as we just learned, is called phosphate. So there you go. There's your name. Yep, that's great. Alright, see here. Nope. And then to go over this part again, the 3, why the 3 got there is because if we separate them out, put them like, if we were to show it separately, we would then realize the charge on this one is +1, the charge on this one is -3, and so the 3 would end up here, the 1 would end up there. And because this is a group, when you put a subscript outside a group, you gotta put a bracket around it. That's why this 3 is there. Just like how you did earlier when we did the more simpler ones like aluminum and oxygen, right? Aluminum is +3. I should say 3 positive. This is 2 negative. So you're bringing these numbers down here, giving you Al2O3. Make sense? Same rule applies. All right. Okay. What else can I do here? All right. I got some questions for you over there to practice. Let's have you do the first one. How are we doing for this one? Aluminum nitrate. Right. So this is one. These are the ones where you gotta write. You're writing the. You're writing the formulas. Aluminum nitrate. Aluminum nitrate. Here, right? So this nitrate on your list you just made. Nitrate is this one. Now comes the charge. Here is 3 plus, there is 1 minus. 3 goes here, 1 goes here. So you end up with this. Is that what you have, Crystal?
No.
Okay, what happened here? 5. Why, how did you get a 5? Oh, okay. So, you always want to try to refer back to here because when you see nitrate, right, don't forget it comes with a charge too. So as soon as you know it's nitrate, and you always want to pay attention to the charge. It tells you there, so you don't even need to figure out, okay, nitrogen and oxygen, okay, what's going to be the charge. Just know the charge off this list. Okay.
Okay.
And how are you doing? What I will do is keep this chart you had close to you, so you can refer back to it, because that's where you will find the charge for the second half nitrate. Yeah. Don't forget to add on the charge, okay, David? This charge should be here, here, and that's what you're going to use for the formulas. So at this point, it would help you not to look at these periodic tables. Okay, you don't have this in handy, right? At this point, how do you become successful at these is to start thinking of them by groups, you know, like reading, you know, you're reading these formulas, just like you're reading a word. You don't start like you know, like word. You don't start analyzing the hair. There's a W, there's an O, there's an R, there's a D. You just see it as one big word. That's how I want you to see these, as one blocks. 1 and 2. Okay? Do another one. Let's do the next one on the list. Copper to phosphate. Copper to phosphate. Okay, take a minute. Yeah, it's okay. You got it. You have to be confident in it. Let's see. Okay, yeah. Let's see, hold on. Okay, so. Yeah. Anyway, the symbol for this is Cu.
Oh.
Yeah. It's okay. Don't worry. And pay attention to the charge on this. Okay. You okay?
Yeah.
Corrected?
So like this one?
Yeah. Now, let me make one thing clear, guys. This should not be a part of your answer. This should not be a part of your answer. The answer does not involve having a chart on top of the element. Okay? I'm only writing these here. This is the like in-between steps that you do to help you make sure what number ends up down here. That's the one that counts. These numbers count. These ones shouldn't be there as the final answer. Right? Which means when you do this one, right? When you do this one, it's a good practice to write out the charge on this. Write out the charge of this one. Right? And then you can start putting it into pieces. And you just gotta go back and erase it out, right? When you get good at it, you don't even need to, like these, then you keep in your head. So you just go straight to the answer and you're done. Okay? But I don't really encourage you to jump to the conclusion right away. I really encourage you to work it out step by step. Right? Okay? Okay. Let's take a break. Found some chocolate.
来，你的。
哦，这什么紫色的？哦，OK。
要凉的吗？
不用不用。
不用。
That's cool.
你们俩喝点水，现在给你热水啊，烫了小心啊。
Let's do that here. So my plan is next week when I connect this onto the TV, I'm going to show you some documentary. There's this very good documentary about all the elements, yeah. So, because today is kind of hard to do that on a small laptop, that's why next week we'll begin with the movie, yeah, you can call it movie. And then we'll see how far that takes us, right? Because right now I'm going to introduce you the next compound, next type of compound. Next kind of compound is called covalent compound. So a different compound would imply the bonds between the elements are going to be different. It's going to be a different type of bond, and they're going to be a different force that keeps the bond together. So we learned ionic compound has ionic bond. That is the attraction between the positive charged and the negative charge coming together. This type of bond doesn't deal with the charge. It has nothing to do with positive signs, negative signs. So kind of like unload what you learned earlier and then start fresh. Alright? That's what you, what does it say? It says, covalent compound form when atoms share. Right. So the key characteristics of covalent compound is that atoms share electrons.
Is that what happened in a ionic bond too?
I will definitely get into this word a little bit because that defines the whole sentence. I'm going to talk to you about what does it mean by shear. Because sometimes the English language fails to capture the true meaning of the bond. So, I'll give you the example we have just learned about. The chlorine, two chlorine atoms coming together. The X are still electrons, I'm just trying to use a different way to draw them. Alright? Pay close attention now, let's count them. If you count them, there's a total of 14, right? Number of electrons is 14. Why is that? Because we learned the valence electron of chlorine is 7. And there are 2, so makes it 14. There's no it does not involve losing electrons or transferring electrons. That's not what that is about. So the whole idea of these compounds are different. The way that goes, how do you understand there's a bond right in between is, okay, let's come back to this idea of shear. What do you mean? What do you think this word means, shear electrons? What does it mean when you share something with other people?
Give them something.
Okay, it's funny you use the word give because that actually more implies like just literally take your stuff, give it to that person. That's actually more like, transferring electrons in ionic compound, right? The idea of share literally means, okay, you can use mine, but I'm still using it. So we're both using it at the same time. That's what we mean by share. Like say, okay, what's a good example? Like we're sharing a car. Like I'm sitting in the car together with you. We're both taking a seat inside the car, but I'm using the car, you're using the car at the same time. That's what's happening with these electrons. All right. So let's the way to count. Okay, so the way to account for the sharing goes like this. So the ones that placed in between, right inside the circle, are the ones being shared. These are the shared electrons. So let's count the number of electrons. Okay, taking into account the shared ones. On the left side, you have 1, 2, 3, 4, 5, 6, 7, 8. Because this one is shared, right? So that means it belongs to him. At the same time, it belongs to the right chloride atom. It also belongs to the left chloride atoms. And so when you go count the valence on this one, you can count 1, 2, 3, 4, 5, 6, 7, 8. Isn't that magical? You can make both satisfied by only having 14 in total. If you don't share the electrons, you would need 18, right? 16. But by sharing it, you reduce the number of electrons necessary to make both parties effectively having full valence. That's the idea of sharing, right? So essentially, you're counting the ones in the middle twice. When you count the valence, right? You count them first time when you're counting the valence for the left side, and then you count it again when you count the valence for the right side. The ones in the middle are shared. And what's also cool about the share is that, just like the word share, everybody is, how do I say this? This electron initially belongs to this chlorine. This electron belongs to that chlorine. So it's gotta be equal to contribution when it comes to sharing electrons. So if one chlorine shares its electrons, then the other party also must share the same amount. That's what that means, share, okay? So here, that's the example. For this chlorine shares its electron, this chlorine shares this electron. That has to be the case for this to work. Equal contribution. Think about at school when you're doing project, right? You have partners. You do some parts of the work, he does some parts of work. You guys must contribute equally, right? For that to be a group project. You can't just be like, okay, I will donate my electrons, you don't need to donate your electrons, and somehow, we can share my electrons. That's not how that's gonna work. If I donate my electron, if I were to contribute my electrons, then my partners also does the same, equal amount. So here, this is what's considered one bond. All right, let's kind of go back on our slide here. What does it say? So the covalent bonds, covalent involves sharing of electron between non-metallic atoms. It's usually non-metallic, right? That's also the key thing. Non-metallic atoms. And right here, sharing of electrons. This is the easier case. This is about two hydrogen atoms. One is, each of them only have one electron. In this case, they share all they have, which is only one electron. And together, they satisfy the octet rule, right? Both of them now have 2. In theory, okay? Because both electrons, one coming from either side, are shared. Which is different than ionic compound when, once this electron transfer over, this side loses that electron. It's no longer his. It's now going to him. So that's the transfer, this is the sharing. And then when it's shared, it's called covalent bond. Okay, so here 2 atoms, boom, 1 bond. Right. During bonding, the non-metallic atoms share electrons and to achieve noble gas configuration, right? So we then go back to our knowledge of the idea of all the elements wants to have the same number of valence electrons as their neighboring noble gas. The closest noble gas to helium is to hydrogen is helium, right? Remember that race I told you about? On both ends, you want to reach the end, like depending on how far you want to go, you determine if you're going to lose electrons or going to gain electrons. That still applies here. So the tendency to want to achieve full valence still applies. It's just now instead of giving and taking electrons, the atoms figure out a different way to achieve the same goal. That's all there is. So they got kind of like, they got tired of switching around atoms, switching around electrons. They decided to share. Okay? Rule 1, this is pretty important, okay? Each atoms must contribute equal number of electrons. That's the one I mentioned. You cannot just have one chlorine donate 2 electrons, which means if this was a bond, right, which it is, and it has 2 electrons in it. Okay, first of all, I guess, you know what? Let's just carry it out. So chlorine, you cannot just have one chlorine putting up all 2 electrons in the middle, and the other one doesn't put up any.
What did you work?
It wouldn't, or it will look like this. I'll show you. Okay, so 1, 2, 3, 4, 5, 6, 7. Yeah, 7. This one has 1, 2, 3, 4, 5, 6, 7, 2, 5, 6, 7. Look at that. Now I still have 14. It's still 14 electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It's still 14 electrons in total. What is changed is that, okay, these 2 are both coming from this chlorine, or it could be this one. Oh no, it's coming from this one. But look, like this chlorine didn't get his partner's electrons, so it only has 1, 2, 3, 4, 5, 6, 7 valence, and that's not and that's not good for him. He's not happy like that. But this side, after receiving 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, this side isn't happy as well. But this doesn't work. You gotta have equal contribution, right? Right, so the correct drawing is, which one is the correct drawing? Alright. Which of the one is the correct drawing? So look at what's going on, right? The X means electrons from one side, the circle means electron from the other side. So in between you have a circle and X, a circle and X, which means this is okay. They are having equal sharing, right? the right side puts up 2, the left side puts up 2. Over here on this side, the left side doesn't put up any, but the right side puts up 2. Not the correct way, right? This doesn't satisfy this rule. So this is not considered a covalent bond because there's no equal sharing. This is okay. Second rule says a bonding pair, which is like basically all the electrons involved in the bond. Let's kind of discuss it, because a bond can only have even number of electrons. Because one side gives up 1, the other side also gives up 1. It's got to be at least even number. It can be odd number, right? If it's odd number, then that means it's not an equal share. So one bond is composed of 2 electrons, 1 from each side. Bonding pair of electrons from one single covalent bond. The bonding pair of electrons. So here's one pair of electrons, right? A pair just simply means 2 electrons. So there is 2, 1, 2, and so we call it a pair, and this pair makes it a one bond. Okay. And so how about you can have 2 pairs? So the number of bond, it's like a relationship 1, 2, 3. Number of electrons 2, 4, 6. These are all possible. So when you see 2 bonds, it just means that in total 4 electrons are being shared. We can I can show you an example of that right here. Oxygen. So each oxygen is going to put up 2 of its electrons, making it overall 4 electrons being shared. So it's going to share 2 from this side. The other side is going to also share 2. And this side, this in the middle, this is the 2 bonds, 2 pairs. So we always think a bond is a pair of electrons. So here you have 4 electrons. Yeah.
Can this bond occur with, like, say, oxygen and sulfur?
Yes.
Or
Yes, it can occur. Yes, you're right. Yeah. Good point. It can be between different atoms. Doesn't have to be. It can be between 2 different elements. Doesn't have to be the same elements. In fact, I can erase this and replace it with sulfur. Right. Go. Right there. That would be the example of 2 bonds, and I have circled 4 electrons inside, right? You can also do 3 bonds. 3 bonds, let's see how is that gonna go. You're gonna have, you have nitrogen putting up its 3 electrons, and then putting the next over here, also putting up 3 of its electrons. When you go and count the valence, what you do is you go like this. So 1, 2, 3, 4, 5. All that's their own, and then count the ones that's being shared. 6, 7, 8. Over on this side, first count the original electrons, their own electrons. 1, 2, 3, 4, 5. Then count the other side, the electrons contributed by his partner. 5, 6, 7, 6, 7, 8. And so here's the example of 3 bond. Now, why do you think this has to be 3? Well, if you try to draw 2 bonds, this simply won't work. You won't be able to allow both sides having 8 electrons if you don't draw 3 bonds. That's why Mother Nature just figured it out that if 2 nitrogen were to bond, in between there must be 3 bonds for that to work. So if we were to try to give nitrogen only 2 bonds, it's not going to work because either side or both sides won't have full valence. 1, 2, 3, 4, like this. This is not 8, okay? So I still have 5, 1, 2, 3, 4, 5, and then 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7. 7. Not happy. Question?
Wait, so for like, can you do like 4 bonds?
Yes. I don't think you can do 4 bonds. No, the answer is no. So you can only see up to 3 bonds at once. Like up to 3 bonds in between 2 atoms. Okay? So you can't do this because this doesn't satisfy octet rule. Doesn't give you the noble gas configuration. Let's try 1, just for the hell of it, right? Let's try if you used to share 1, then you still don't have full valence. This is 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5, 6. Nope. So that's not gonna work. Yeah.
Can you can the atoms share all of their electrons?
It doesn't need to. If it does, look what's gonna happen. So nitrogen here, if it does, then all 5 are being shared, right? So 1, 2, 3, 4, 5. On the other side, 1, 2, 3, 4, 5. Then it's too much electrons.
With something like carbon and silicon.
Yeah.
So would that work?
Okay, let's see. Carbon and silicon. No silicon. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. Okay, I see what you mean. Like this.
Yeah.
Let me see. Theoretically, it can. All right, theoretically, it can. You're not wrong. I mean, by theory, this should work. The only reason that it doesn't work is the definition. Okay, we're trying to work within the correct definition. Atoms. So the definition about a covalent bond technically means a shared electrons between 2 non-metal. I mean, at least 2 non-metals atoms. Now, carbon is not a metal. It's not a non-metal, right? So it's not really a non-metal either. So A doesn't satisfy the requirement. Silicon, is that a metal? It's not a metal, but it's not a non-metal either. So I mean, you don't actually if this compound were to exist, you don't call this a covalent bond. So it doesn't satisfy the requirement for it to be a covalent compound. Make sense? Because not only is the periodic table just non-metals or metals, it's got metalloids in between. Remember those? Yeah, you gotta remember those. So I believe carbon and silicon are both. I think carbon. I'm not sure. Carbon may be non-metal, but silicon is definitely not metalloid.
Silicon is a metalloid, but carbon isn't.
Yeah. Atoms share electrons amongst non-metallic atoms. There you go. All right. What's next?
Wait, what happened if there's like 2 carbons?
Yeah, then No, you know what? Carbon that doesn't do it like that. Carbon in real life doesn't combine with one partners. Carbon in real life goes like this. And then it keeps on going. You know? Do you know what I'm trying to get at? It doesn't form bond with one other partners only. It doesn't form bond with only one partner. Carbon likes to do single bonds and then have the other three bonds between other partners. Alright, so it's like this very popular person doesn't like to only hang out with one person. Likes to keep a lot of friends around and share a good connection with all of them. That's the idea.
But can't carbon technically like have a covalent bond with the bottom element?
Which one?
The atomic number is 114.
Yeah, but then I don't think that's a non-metal.
I mean, they don't know much about it, so it could be like a gas or something.
Yeah, maybe. I'm not sure though. I don't know that much to know like for sure if there's a bond here. Yeah, so carbon doesn't. Carbon is pretty popular. Like it doesn't do this type of bonding all that much. I mean, not with its own kind, anyways. With its own kind, it does this. It likes to. It's got 4 electrons. It likes to put up 1 electrons to each of its partners, each of its neighbors, and so it's gonna have 3 other neighbors. 4 other neighbors, 1, 2, 3, 4, in between having 1 shared bond, or 1 bond. And so that's the part we can get into next time when you can have a group of more than 2 atoms, all sharing bonds. Right, like your neighbors, you have neighbors on your left side, on your right side, on your backyard, front yard. You can be good friends with all your neighbors. That's the idea. You don't need to just hang out with your one neighbor. You can hang out with someone else too. Okay. We've been drawing this Lewis dot diagram. Everything we've been drawing over here on the board was really just these Lewis dot diagrams. Okay. Another way you can draw it, this only applies to a covalent bond. You can simply, instead of showing all these unshared electrons, we just forget them. We just ignore them. We can just draw between 2 chlorine just 1 line. 1 line to represent the bond. And this line, it means 1 bond, which you now know it really is 2 electrons. Like this. So 2 bond would be like, 2 bond would be like this, 2 lines, 3 bonds like this, 3 lines. And obviously you're visualizing 2 lines equals 4 electrons, 3 lines equal 6 electrons. Okay? This is an even simplified drawing than these. Yeah? This kind of drawing is called structural formula. Where it's just using a line to indicate the bond. And so carbon likes to do this a lot sometimes. 1 bond here, like you can do hydrogen, hydrogen, carbon, hydrogen, keeps on going, hydrogen, hydrogen, carbon, hydrogen, you can keep going. You can have a gigantic, you can have a gigantic molecule like this. Then we're getting into very, very big, like a compound with 100 atoms. It's possible when you're dealing with carbons, because their tendency is to hang out with a lot of other atoms. And you can start to make out the shape, right? It's like it's got like curve, right? You know, like this. Anyway, that's why, you know, that's the name of this kind of drawing, structural formulas. But you can also see carbon do this, right? Share 2 electrons with oxygen. That's also possible. Okay. Alright, let's move on to. So I want you to try draw some of these. We learned now, for as far as covalent bond is concerned, you have 3 ways to draw them out. You have the Bohr-Rutherford. I'll show you. Rutherford looks like this. So yeah, we just saw it. H, hydrogen. Well, you know, you gotta really be, if you really want to be specific, you can put inside here 1 electrons. The other one is also here, protons, another electrons. Oops. Yeah, that's pretty much it. That's the bond. Here and here. That's the Bohr-Rutherford diagram. I don't really, this is just gets really tedious having to draw so many circles. It's not really recommended. This is the most recommended one, and then this. So I mean, to be honest, I will only require you to draw the Lewis dot and draw the structural formula. So give you guys some chance to practice from those questions. Let's take for example, let's take, okay, let's try to draw number 5, carbon dioxide. You see, carbon dioxide, this one here.
Isn't carbon dioxide already a compound?
Yeah, that's why you're trying to figure out where to place these compound. Okay, you know what? Yes, I gotta give you some clue first. So carbon dioxide looks like this. It's got 1 carbon, 2 oxygen. Okay. So you can start filling in electrons in between them. Actually, hold on. I need to give you an example how to do these yet. Okay, so we're gonna come back to this example, right? Let's try. There's a way to get at the right answer properly. So let's do this example here: sulfur and oxygen. You know, obviously they're gonna be a bond, at least 1. You don't know if it's gonna be 2 or 3, but you start with 1 and see if it works. So I have 1 here, another 1 here. Yeah, and then did you wrote these down? Write these down?
Yeah.
Okay. Okay. 1, 2, 3, 4, 5. Alright, forget about this. There is a way, there's a very quick way to know how many bonds that should go in between. It goes like this. So you still need to know the charge, right? The charge that goes on the atom. So we're gonna say, okay, this is -2, yeah? This is -2. That 2 tells you how many bonds there needs to be in between. Okay? So let's say, okay, so to determine the number of bond between atoms in covalent compound, first, well, not first, like to determine the number of bond between covalent compound, find out the charge of the atoms or the elements. That's the tip. As long as you know the charge, you will be able to figure out the bond. How many bonds? What's the charge on nitrogen? Yeah, keep going. Yeah, what's the charge on nitrogen?
-3 negative.
Yep, good. Does this make sense? 3 bonds? Yeah? So this rule applies. Okay? No exceptions. I mean, you won't see this rule fail you. Okay, it's generally pretty good. Oops, this is wrong. Erase this, okay? Erase this. So what happens when you are trying to make a covalent compound when the participating elements don't have the same charge? Like here, both of them are all the same charge, right? But how about what if like the elements don't have the same charge, which happens a lot. So let's say, by the way, covalent compound includes, you can have compounds involving hydrogen. Because like we said, hydrogen is not a metal. Although it's in group 1, it's a non-metal, okay? So you're gonna see a lot of the times a covalent compound with hydrogen in it. In fact, let's take that right now. So hydrogen, let's say I wanna make a compound between hydrogen and I wanna make a compound, hydrogen with carbon. So this rule is a bit fuzzy then, right? Because then it doesn't quite tell you right away how many bonds there should be. So now carbon needs to lose a charge. It needs to become positive. You know what? Hydrogen is not a good example. Let's use fluorine. Fluorine with carbon. Okay? So fluorine is -1, carbon is then -4.
That's 4.
Honestly, in this case, Carbon is pretty ambiguous. You don't even need to write the sign. Just know that it has to do with 4. Okay, because you know, as we learn, anything following anything in this group, in this family, you can lose 4 or gain 4, right? So what you're gonna do is because fluorine only needs 1, only needs to fluorine only needs 1 bond. Doesn't need any more, but carbon needs more bonds. Because look, chlorine is 1, so chlorine only needs 1 bond, right? Based on its charge. Carbon, on the other hand, needs 4 bonds. So how is this gonna work? You can't shove bonds to fluorine when it doesn't need it. Yes.
Why don't we just add 3 more fluorine?
Exactly. Very smart. So that's exactly what happened. So go like this. 1, 2, 3, 4. And there you go. And carbon gets its 4 bonds because he gets it from 4 different fluorine atoms. 1, 2, 3, 4. That's how that works.
How do you draw a Lewis dot diagram for that?
For this, so here you go. 1, 2, 3. Like this. That's a lot of dots. So this is much clean. It's a lot like it's simpler to draw, much faster, looks a lot cleaner. Okay, so the formulas for the chemical formula is this one here, CF4. Now let's have you go back to carbon dioxide and finish that drawing. Let me see. Yep. Yep, it looks okay. Yep. You can make another roll for these 4. You can break it, move the X underneath. Like you can move these, instead of drawing all 4 electrons on 1 line, you can draw them on 2 lines.
Okay.
Yeah. Yeah, that works too. So the orientation, like if you're doing it vertically, sideways, horizontal, there's no rule again. Like there's no doesn't matter how you draw it, right? Okay, so carbon, you can do it like this too, or you can do what David did. You can do it like this. Like you can do like here, 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 it doesn't matter. There's a gazillion ways to draw these. But we're gonna do like this, side, like horizontally. So very quickly you figured out that carbon's charge is 4, oxygen charge is 2, and so you're gonna need to bring another oxygen to make this work. And then you obviously figured out that within each bond, in between each here, there's going to be 2 bonds, right? So here, here, okay. Here, here, 1, 2, 3, 4, 1, 2, 3, 4. And so 2 bonds here, 2 bonds here. And then the structural formula looks like this. That's carbon dioxide, right? And then if you picture the 3D, actually how it looks, oxygen looks like this. Carbon in here, oxygen on the side. It's a rectangular looking molecule. That's all the gas, that's the whole idea. I mean, that's how it actually looks like. It looks like this. But tiny, tiny, small shapes like this. Okay? Alright. So, let's see if I can give you another one to draw. Yeah, let's try how to draw water. Yeah, so we've been talking about water. Yeah, H2O, this is a covalent compound, okay? Now you finally can put a word around what type of compound water is. It is covalent. Let's analyze this word a little bit too, right? Because you want to make sense. You want to use many ways to enforce your knowledge. Co means the same. Cooperation, right? Means same. Valent. Doesn't this word kind of ring a bell a little bit? We learned about valence electron. Covalent means they gotta have the same valence. Essentially, both parties gonna have the same valence, meaning it's gonna reach full valence. That's the same valence compound. And co means that it implies both parties needs to put up the same number of electrons to form the bond. You want to check your answers? Looks almost okay. What does the rule tell you? How many electrons per bond? How many electrons per bond? Guys? 2 electrons per bond, right? And what is one line represent?
1 bond.
Right. So you got 2 electrons per bond, 1 line is 1 bond. So how many bonds should you have? Yep, that looks good. Okay. Alright, like try to get used to try to get used to translating from this to this. Okay? Because you see 4 electrons, that means 2 lines. Right? If you see only 2 electrons, that means 1 line. So this is the part that takes a bit of getting used to, because that's one of the rule. 1 bond is 2 electrons, right? And so on and so forth. Okay, so good job. This is good work. Hydrogen, water, and yeah. Alright, what time is it? Alright. So I guess we'll wrap up here. Next week we'll start with some videos to watch.